In this video series, we're going to look at the area of triangles. And in part one of this video, we're going to take a look at the area of triangles in a plane. Then we're going to figure out the area of triangles in a coordinate plane. Later in part two, we'll take a look at how lines intersect and the regions that they form. So in the first part, we're going to look at the triangles in a plane. We know that the area of a triangle is 1/2 base times height. Now the key here is that we have to have a right angle somewhere. The base and the height are the sides that form the right angle. So let's take a look at an exploration of why this actually works. So here we have a drawing here, a sketch. The area is 1/2 base times height. We've got this triangle. There's clearly our base, our height. We can move some things around, or we can move some things around, and it doesn't seem to change much, okay? What we're going to do is we're going to take that diagram and we're going to rotate. And when we rotate those, again, these are just the pieces of the triangle, rotating them out. And when we do that, we now get a rectangle. And we know that the area of the rectangle is just the base times the height. Well, here's the cool part. If you go backwards and unrotate it, essentially we're going to take away this shaded area, which has exactly the same area as that triangle. And so that's why the area of a triangle is 1/2 base times height, because it's just half of that rotated rectangle. So let's apply it now. Again, we need to have a right angle in order to make this work. And in number one, we already do. We have sides of 3 centimeters and 4 centimeters. So when I want to find the area of this triangle, I'm going to do 1/2 of 3 times 4, which is going to give me 6 centimeters squared. The perimeter is all of my sides added up. So if I know one side is 3 and another side is 4, and I know it's a right triangle, then the hypotenuse has to be 5. That's just one of our triples, 3, 4, 5. So the perimeter is just all 3 added up. 3 and 4 is 7, plus 5 gives me 12 centimeters. Number 2, we've got our right angle set up, and it's not just like number 1, because it's a different location for that right angle. That right angle now is inside the triangle, and it forms an altitude. So the altitude is going to be part of what we need. And think of altitude as your height. Interesting how that works out. And that's going to help us try and find out what the area is. But to do that, we need to find the base. Well, here's the thing. We have a right triangle right here that we can solve this little piece there. And I can use the Pythagorean Theorem. If I know it's a triple, which I happen to know, that's a triple with 12 for a missing side. And we can do the same on the other side. We have a 9 here, and there's a right angle there, because again, we're forming a straight line, so the two angles have to add up to 180. The triple with 9 and 41 would give me 40. So my entire base then is 52. So when I'm finding the area of this triangle, I'm going to do 1/2 of 52 times 9, which is going to give me 1/2 of 468. And so 1/2 of 468 is 234 inches squared. And then the perimeter, I'm going to add up 52 and 41 and 15, just the outside pieces. When I add those up, I'm going to get, let's see, 52 plus 41 is 93, plus 15 would be 108 inches. In number 3, we have what's called a obtuse triangle. So that angle between the 10 and the 12 is hopefully clearly larger than 90 degrees. So again, to find the area, we want the base and the height. The reality is we already have it. Now, what's strange about this is that the height of the triangle is actually on the outside, and that's our altitude, which in this case is 8. We're still going to use that as our height. We're not going to go inside the triangle because we simply can't, based on that obtuse angle. So my base is going to be 12 because that's the part of the triangle that I need. And my height is 8, so I end up getting 48 square centimeters. Notice that when I'm finding the base, I'm not including that little dotted segment because that's not really part of the base. And the 8 technically isn't really part of the triangle. We're just using it as a reference to find the area of it. then the perimeter is the three sides here added up. So again, I don't even need to know what that is. It's 6, by the way, but I don't even need to know it. So I just need these three added up. So I'm going to take 10 and 12 is 22, plus 15 gives me 37 centimeters. And let's talk about number 4, and then we'll get into the idea of encasement and what that is. Number 4, it looks like we don't have a right angle, but we can create one seemingly out of nothingness. We're going to take our angle right here, and we're going to drop straight down an altitude. Now, the fact of the matter is this original triangle was isosceles because of the two equal sides. So when I drop that altitude in, we know that if we have an altitude in an isosceles triangle, that it's also the median. So that 4 is going to be cut into two equal pieces. So they're both 2's on either side of that altitude. Now, what I need to do is I need to find out what is the altitude and what does it actually measure. And to do that, I'm going to use the Pythagorean Theorem. So I'm going to take 2 squared plus, we'll call it h squared equals 5 squared. So we have 4 plus h squared equals 25. H squared is 21. So then h would be the square root of 21. So that's my height right there. When I'm finding the area, then I'm going to take 1/2 my base. The whole base here is 4, and then my height is the square root of 21. So my area is 2 root 21 centimeters squared. The perimeter, again, is just the outside pieces added up. So I don't need the altitude when I'm finding the perimeter. I'm just going to take 5, 5, and 4, which is going to give me 14 centimeters. Okay, so let's take a look at activity 2, or the second part of what we're going to take a look at, which is what happens when we have them in a coordinate plane. How do we find the area of these triangles? So in Model 1 and Model 2, we have seemingly different right triangles, or sorry, seemingly different triangles, and they are for a very important reason. Now we know that the area of a triangle is 1/2 base times height if we can get a right angle out of it. And again, in this one we can, in Model 1, if we just drop an altitude right from that vertex. So we need to know what's the base. Well, let's see, 1, 2, 3, 4, 5, 6, 7. And our height is 1, 2, 3, 4, 5, 6. So when we're trying to find the area of that triangle, I just take 1/2 of 7. I'll use it one time, times 6, which would give me 21. In Model 2, though, I don't know if I have a right angle. I'm suspicious about that corner up at the top. It looks like it might be a right angle. But if I investigate further, it won't be, because my slopes will not be opposite reciprocals of these two lines. If it kind of went through the grid points here, then it would be, but it's not. So I have to come up with another way to do this. And this is where the idea of encasement comes around. And essentially what it is encasement is going to be taking any shape that we have, putting a rectangle around it, finding the area of that rectangle, and taking away what you're not actually going to use. So I'm going to look at my high points and my low points. And it looks like my low point is right here. That's my lower corner. My high point is up here. So I know when I'm drawing my rectangle, I'm going to go from here to here at a bare minimum. But I need more than that because I don't have a rectangle yet. So then I'm going to look at my far left point, which is over here. So I know that when I continue this rectangle, I've got to at least go through that point. So now what ends up happening is within that rectangle, we have 3 smaller triangles that we're actually not going to use, but we're going to use them to find the area of the original triangle. But to do that, we need to know the dimensions of the rectangle first. So let's see, we've got 1, 2, 3, 4, 5, 6. And we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for that side. So together, the area of that rectangle is going to be 60. So I know at a maximum that area of that triangle can be 60, but I know it can't because there's some things I'm not actually going to use. So we're going to take away those triangles that we're not using. So to do that, I'm going to use my dimensions here. I got a 10 and a 6, which is important information, because now I can figure out the other triangles. This is a height of 1, and this then would have a height of 5, because they have to add up to 6. The opposite sides must be equal. And then I've got 1, 2, 3, 4, 5. So if this is a 5, then so is that. 5 and 5 gives me 10. So now I've got 3 triangles. I've got this one here, this one here, and this one here that I'm not going to include. So I'm going to find the area of each one of those, and I'm going to take them away from the rectangle. So this triangle has an area of 1/2 of 5 times 5. And I'm just going to go with a decimal here because it'll make it easier in the end. So we're going to call that 12.5 for that triangle. I do the same for the blue triangle. So 1/2 of 30, so that's 15. And here I have 1/2 of 10 times 1, which is 5. So now I have my triangles that I'm going to take away. I've got a 12.5, a 15, and a 5. Together, that's going to give me 32.5. So everything all together is 60 for the area. But we're not going to include those 3 triangles. We just needed them for reference. When we subtract those away, what we're left with is this triangle in here, which we're trying to find the area of. So if we take 60 minus 32.5, we get 27.5. And that is the area of that triangle. So again, that's the idea of encasement. We just take that big rectangle, take away what you're not actually going to use. And again, 1/2 base times height to find those missing or those triangles that we're not going to use.